Okay, this is going to be the video for examples for lesson 10, where we're considering the normal model and also normal approximations to binomial in one of the examples. There are a lot of different kinds of things we can do with normal distributions, so I'm trying to just do like one problem of each different kind of problem that you might see here. Okay, the first problem says, some researchers believe that intelligence can be measured and reported as IQ, or intelligence quotient. Standard tests of IQs show that IQ score varies approximately normally with a mean of 100 and a standard deviation of 15. The word genius is used to describe people whose IQs are at least 125. So the questions are, what percentage of the population would be classified as genius level? And then B, if a group of 100 people were randomly selected, then how many people in that group would you expect to be geniuses? So pause the video and give this one a try. Okay, so for A, we're talking about a normal distribution here. So whenever we do that, I always go ahead and sketch a normal distribution. I'll put the mean here. The mean value is 100. And the standard deviation, which would be right around here, is 15. That means 15 above and 15 below. That's the average distance the data is from the mean of 100. It also means that as far as the scale goes, this value here would be 115, and this value here would be 85. All right. So we want to know what percentage of people would be classified as geniuses, and they said that geniuses would be people with IQs of at least 125. So if this is 15, if I want another 15 out here, that would be 130. So 125, I'm guessing, would be roughly here, right around there, 125. Right? Now this tail for this normal curve actually goes on forever, right? This is an exponentially based function here, so it actually never quite touches zero, and that means that, let me actually draw the end of this a little bit better to exaggerate this a little bit. I'll make it go like that, and that means that if 125 is here, then there's a number of people out here that would be considered geniuses. It would be the area of that curve, and actually this goes all the way out to positive infinity. It'll be a vanishingly small number after we get a couple, 3 or 4 or 4 or 5 standard deviations away from the mean, but it does go off to infinity. Okay, so we have a couple of calculator functions that allow us to find this area under this probability density curve, so we don't have to resort to calculus. We can just say that the probability, or the percentage, I'm going to write it as a probability, that an individual person would be classified as a genius and have an IQ above 125, we can use the normal CDF function for that. So the normal CDF function accepts a lower boundary, an upper boundary, a mean, and a standard deviation. So the lower boundary of this shaded area would be 125. The upper boundary would be infinity, so I'm just going to put a very large number in, like 999. And then the mean would be 100, and the standard deviation would be 15. And that we can use TI-84 to calculate, or 85. If I go to the distributions submenu, second variables, the second item down is normal CDF. And we'll set the lower bound to be 125, the upper bound to be something representing infinity, with a mean of 100 and a standard deviation of 15. And that turns out to be 0.04778 approximately. So this value, this probability or fractions would be 0.0478, which is about 4.78%. Okay, and it did ask us for percentage, so I'll report that as a percentage. 4.78% of the population are considered geniuses, assuming the population follows this normal curve as described. In the second part, it says, if a group of 100 people were randomly selected, then how many people in that group would you expect to be geniuses? Well, if I have 100 people, and I just need to take 4.78% of that, I just would multiply that by 0.0478. And that's just going to give me the number 4.78 people, which means since I can't have 0.78 people, I might just round this and say 5 people. Right? I would expect about 5 people to be geniuses in a group of 100 people. Okay. So let's take a look at the next one. This one says, nationwide, ACT scores are distributed normally with a mean of 20.9 and a standard deviation of 4.8. SAT scores are also normally distributed with a mean of 1026 and a standard deviation of 209. two students are under consideration by an exclusive college admissions board. Student 1 took the ACT and scored a 31. Student 2 took the SAT and scored a 1510. If the students are equivalent on other measures, then which student should be offered admission to this college based on the scores? So pause and give this a try. Okay, so what we've got here is two different distributions. We have ACT and we have SAT, right? They're normally distributed, so both of them have this sort of a shape. And the ACT has a mean of 20.9 with a standard deviation of 4.8. And the SAT has a mean of 1026 with a standard deviation of 209. Okay, so then we have these two students. So the student that took the ACT scored a 31. So if I kind of mark this on here, this would be roughly 20, let's say approximately 25 here. This one would be let's see, that's 26, about one, what is this? 1, 2, and then 15, so 35, 12, 35 for one standard deviation above the mean. So this score of 31 for the ACT is definitely more than one standard deviation above the mean. It's somewhere out here, 31, right? And the SAT score of 1510 is also somewhere out here, right? The question is, which one is more unusual in the context of their own population? So a great way to solve that would be to find what we call the z-score. The z-score is the number of standard deviations that we are away. So if this score was 31 and the mean was 20.9, we could take the subtraction, figure out the difference, and then divide by the size of a standard deviation, right? I'm using the z-score formula, which says that z is the data value minus the mean of the distribution divided by the standard deviation. It just converts a data value into a number of standard deviations. And that turns out that the ACT score's z-score, right, it turns out to be 2.104. So we are 2.1 standard deviations higher than the mean. Okay, the SAT, we could calculate a z-score as well. That would be the score 1510. Here's the mean at 1026, and a standard deviation is 209. So if I took that distance, the z-score for the SAT turns out to be 2.316, right? So although they're both really good, more than 2 standard deviations above the mean, the student that was 2.3 standard deviations above the mean was slightly better. So we would say that the second student, the SAT student, the student number 2, would be the one that should be offered the spot. Okay, let's try another problem here. It says if ACT scores are normally distributed with a mean of 20.9 and a standard deviation of 4.8, then what score would a student need to be in order to be A in the top 10% of scorers and B in the top 2%? So pause and give this one a try. Okay, so on this problem, we're going to draw a distribution like we did before. We have the mean is 20.9, standard deviation is 4.8, which means, this would be, what is that exactly? 25.7. And this one, if I subtract 20.9 minus 4.8 this is 16.1. So I have a scale here. All right, so I'm trying to say what score would put me in the top 10%, right? So the top 10% maybe is this much. I'm trying to kind of estimate how much of that area under the curve is 10% on the upper side. So maybe like that. So my goal is, I know now that this area is 0.01, sorry, not 0.01, 0.10, 10%, 0.10, and this boundary is what we're after. So unlike the problem where we used normal CDF before, where we could use normal CDF to go from a boundary or boundaries to an area, we need a different calculator function to go from area to a boundary, okay? And that function is the inverse normal function. Inverse normal function, we have to put the left area in along with the mean and the standard deviation, and what it returns is the upper boundary of an area. It returns the upper boundary. Okay, so here, let's see, I could use the inverse normal curve to find this, or inverse normal function. Okay, I need to have an area to the left of that boundary. So here's the boundary I'm looking for. The area to the left of that would be this green area, right? So hopefully you can see that if 10% of the area is to the right of the curve, then 90% of the area would be to the left of the curve. So I'm going to put 0.90 in for the area to the left of this boundary. And then I'll enter the mean, 20.9, and standard deviation, 4.8. And then we can have the calculator tell us what the value is. So if I go to that same location, second variables to get to the distribution, remember the third item down is inverse norm, right? Area to the left is 0.9, so I'll enter that as a decimal. And if the mean is 20.9 and the standard deviation is 4.8, then that gives me a boundary value of 27.05. So this value here would be 27.05. Okay, so in other words, if I wanted to be in the top 10%, my HCT score would have to be a 27. I'd have to have a 27 to be in the top 10%. All right, and for part B, we're going to do something very similar, right? The only difference is I still have my same 20.9 and 4.8 standard deviation, but this time we're going to be in the top 2%, so that's an even smaller region out here. We have a boundary further out, so I'm expecting the score to be higher, where I have only 2% of the area up there, not 10%. So if that's 2%, then the area to the left this time would be 100%, take away 2% is 98%, and that means that the calculator function we would use is inverse norm. If the area to the left is 98% with a mean of 20.9 and a standard deviation of 4.8. And so that turns out to be same function. I just want the area to be 98% this time. And so that tends to be out to be 30.7. 30.7. Okay. So if I wanted to be in the top 10% of HCT scores, I would have to have a score of 27. 30.7 would be a top 2% score, the lowest of the top 2% scores. Okay, let's go ahead and move on. So 10.4, this fourth problem, it says in a standardized normal distribution, what z-score has 20% of scores above it? So go ahead and pause and try this problem. Okay, so just a little background. If you have z-scores, let's say we have data, like that data for IQ, 100, and standard deviation of 15, right? The z-score formula, we said, is take the data value, subtract the mean, and divide by standard deviation to convert to a number of standard deviations that we're above or below the mean, right? So if I decided to do that, what would the z-score value be for this data point right at 100? Well, that would be 100, take away the mean of 100 divided by 15, and that would be 0. So that means that this data point translates into 0, right? If I were to pick a point that was +1 standard deviation above the mean, which would be 115 over here, the z-score for that would be 115 minus 100 divided by 15. That's going to be 15 over 15, which is 1. Makes sense because z measures the amount of standard deviations we are above or below the mean. So this is going to translate to the 0.1. And what that means is whenever I'm talking about z-scores, no matter what the original data set is, the mean is always 0 and the standard deviation is always 1. Okay, so all I need to do to solve this problem is to say, all right, let's draw a standardized normal curve, which has the mean at 0 and the standard deviation set at 1. This is from +1, and this would be -1 standard deviation. What z-score has 20% of the scores above it? Okay, so if I draw something where 20% is above it, maybe I would draw a line here. I'm after a boundary value where this area is 20% here. Okay, so just like the last problem, the area to the left would be the remaining 80%, and I could find that with my inverse normal function. Inverse norm, 80% to the left, but this time I'll use 0 for the mean and 1 for the standard deviation, and that turns out to be 80% to the left with 0 as the mean and standard deviation means that I would be at 0.8416 standard deviations above the mean. right? So this would be 0.8416 standard deviations above the mean there. Okay? So questions about that? Um, sec here. All right, so let's keep going here. The way I would interpret that, you could label that as a z-score. And I mean, sometimes I'll even put a sigma here to remind me that whenever I'm working with z-scores, I'm really talking about the number of standard deviations. So I guess I didn't have my picture drawn right. Actually, this wasn't really correct. I drew this here further than 1, but actually it was 0.8. So this isn't quite the right location. It's really here, 0.8 standard deviations away. That's where 20% of the data is. So I didn't quite sketch it correctly. Okay, let's keep going here. The next problem says the weights of healthy adult Labrador retrievers are normally distributed with a mean of 7 pounds and a standard deviation of 6 pounds. What percentage of these Labrador retrievers are A, between 50 and 85 pounds, B, below 50 pounds, and C, above 80 pounds? Okay, so pause and try this problem. All right, so each one of these, I think we're going to need a normal distribution. Let's go ahead and draw a sketch here for A. It says that normally distributed with a mean of 77 pounds, so that'll be the middle. Standard deviation of 6. As far as the scale goes, if I added 6 to 77, I would get 83. And this over here would be 77, take away 6 is 71. All right. So I'm talking about between 50 and 85 pounds. So the upper boundary would be maybe about here. And say 70, 60, 50 would be way out here somewhere. I'm going to draw it way out here. And so if I'm talking about the percentage there, it would be something like that. So I'm expecting this number to be, something quite a bit larger than 50%. And in fact, actually, it looks like nearly the entire distribution except for a little tail here. Anyway, we don't need to guess. We can say that I could even write it as a probability statement. The probability that the golden retriever will be between 50 and 85 pounds, between 50 and 85 pounds, would be the normal CDF function. And for the lower bound, we'll put the 50. And actually, let me do this below so that we can do these side by side. Normal CDF, and then 50, and then the upper boundary is 85, and then the mean is 77, and the standard deviation is 6. And if you plug that in a calculator the same way as we showed earlier, 0.9088. So about 91%. So we were right. It took up most of the curve. One of the benefits of sketching like this is you get a sanity check on whether your answers make sense. Okay, for B, it says what's the probability that, or a percentage of Labrador retrievers that are below 50 pounds. So I'll make the same sketch. 77, right? Let's see, 6 for the standard deviation. So this goes plus and minus 1 standard deviation, 71 and 83. And I'm looking for something to be below 50 pounds. Okay, so way out here there's 50 pounds, and there's some little bit of area there to the left. Okay, so the probability, or the percentage, or fraction of the population that has the data value below 50 would be normal CDF. But then this 50 is now the upper boundary. The lower boundary would essentially be negative infinity. So I'm going to put a very large negative number, negative 999 in there, up to 50 with a mean of 77 and a standard deviation of 6. And if you plug that in a calculator, let's actually show you what that looks like. So if I do normal CDF from negative infinity to 50 as the upper boundary with 77 as the mean and 6 as the standard deviation, turns out to be 3.6 e negative 6. So that doesn't mean error, that means scientific notation. So it's saying 3.4 times 10 to the negative 6. So that's like a 3.6 where I've shifted the decimal point left 6 times. 1, 2, 3, 4, 5, 6, there. Is that right? 1, 2, 3, 4, 5. Actually, one more 0. So the decimal point isn't there. It's one more. So this is very small indeed, probability. Extremely small, which makes sense because we're so far out on the left tail of this distribution. Okay, I'm going to use the same sketch to do C. I'll just change colors. So for C, we're going to be above 80 pounds. So 80 is maybe right about here. And so the probability would be this part. So again, I'm going to use normal CDF. This time the 80 is the lower boundary, and the upper boundary would be positive infinity. So we'll put a big number like 999 in there with a mean of 77, and 6 is the standard deviation. And if you plug that in a calculator, that turns out to be 0.3085. All right, and again, that kind of matches the sketch. That green looks to be roughly a third of the distribution. All right, so let's move on. The sixth problem here says, at a local grocery store, the average weekly grocery bill is $132.45 with a standard deviation of $38.15 and is normally distributed. What are the largest and smallest amounts paid by the middle 50% of people who shop at this store? Okay, so pause, try this, and unpause the video. All right, when I look at this, I just notice that they gave me the average, which is the mean, and the standard deviation. So I'll go ahead and just start sketching. Normal curve, we have $132.45 with a standard deviation of 38.15. Okay. If I wanted to kind of fill something in here, if I added 38 to 132, this is approximately $171. And if I subtracted 38 from 132, this is around $94. Okay. So we want to know what the largest and smallest amount paid by the middle 50% are. Okay, the middle 50%. Well, I know that if I go to these locations, this is a location that is plus, this is the mean. This is the mean plus 1 standard deviation. This is the mean minus 1 standard deviation. And in general, this right here, the amount of data that's within plus and minus 1 standard deviation of the mean, we know that's 68%, right? So if I were to try to figure out where the middle 50% is, it's not going to be at 94 and 171. It's going to be somewhere inside those boundaries, right? This is where the middle 50% is, okay? Something less than that. So I'm after these two values, these two boundary values. What is the largest and smallest amounts paid by the middle 50%? Okay, so I think what I'm going to have to do is divide. Let me go off on the side and sketch this over again, and then we'll attack the problem. So we've got 132.45 as the mean. We have 38.15 as the standard deviation, right? So hopefully what you'll agree is, if I have the middle 50% here and it's centered around the middle, then that means there's 25% left over on each of the sides, right? And so what that means is if I want this first value here, this left value, I'm going to draw it over here. It's right about here. That's really the first quartile, what we would call Q1. And it means that the area below that is 25% of the data. And the calculator function that tells me the boundary if I have an area is inverse norm. So I could say that Q1 here, the first quartile, is going to be inverse norm, some boundary where 25% is to the left if the mean is 132.45 and the standard deviation is 38.15. So if we plug that in a calculator, this is inverse norm, right? And it would be 0.25 to the left when the mean is $132.45 and the standard deviation is $38.15. Okay, and so that boundary would be 106.72. Okay, so this boundary is 106.72. So that's the lowest amount that's paid by the middle 50%. Okay, and if I wanted to find this value, the upper value, I could draw that on here in the same sketch. That would be called Q3. And for Q3, we would have 75% of the data is below that, right? Because the middle 50% is everything is below that except for this last 25%. So for Q3, I could also use inverse norm. The only thing I would change is I would change this to 75% to the left. 132.45 for the mean and 38.15 for the standard deviation. And that turns out to be equal to $158.18 when you plug that in the calculator. So those are the boundary values for the middle 50% of people who shopped at this grocery store. Okay, let's try another one. They're getting steadily harder here. There's only a couple left, I think. 2 or 3 more. Yeah. So this one says golf balls must meet a standard for distance traveled. Balls are tested using a standard mechanical ball hitting device which strikes all the golf balls in the same way. When hit using the test machine, the distance the ball travels must not exceed 290 yards. Golf ball manufacturers want to develop balls that will travel as close to the 290-yard limit as possible without going over the maximum distance. One manufacturer has a process which allows it to change the composition of the ball's core to tune the distance the balls fly on average. But there is still random variation in the distance traveled from ball to ball. This variation is normal, in other words, distributed normally, with a standard deviation of 4 yards. So A, if the manufacturer sets the mean distance traveled to 284 yards, what's the probability that a ball randomly selected for testing will travel too far? And B, if the manufacturer wants to be 99% sure that a randomly selected ball will not exceed the maximum distance, then what is the largest mean distance they should set the balls to use in their manufacturing process? So this is a tricky problem. Go ahead and pause it and give it a try. All right, so let's attack the first problem. It says that we want to have, we want to evaluate something about the probability. So that means a hint that I'm going to be using a normal curve along with a normal CDF function to find a percentage or an area under the curve. So I'll start with a sketch. Right? They said we did set the mean to 284 yards. So we can tune this value, and we set it to 284 yards. This said the variation is always normal with a standard deviation of 4. So if I put 4 there, that would be like that. That makes the +1 standard deviation 0.288, the -1, 280. Okay? And we want to know what percentage of the balls would be too far. So too far means that we went above the limit of 290 yards. So 290 would maybe be right around here. And so this percentage of balls would be above that limit. So I could use a normal CDF function to calculate that, right? Normal CDF, if the lower boundary is 290 out to something representing infinity, 999, when we've tuned the mean to 284, and we have a 4 for the variability there for standard deviation. So normal CDF, that would be from 290 to something representing infinity. If we've set the mean of the ball to 284, and we have 4 yards for the standard deviation. So that would be 0.0668. 0.0668. So it says, what's the probability? There's about a 6.7% chance that if the golf inspector team came to monitor your manufacturing process, that 6.7% of the time they would get a ball that was too far, and I don't know what they would do. You'd have to pay a fine, or you'd have to shut down and recalibrate your machines or something like that. So presumably that's something to be avoided. But it's only going to happen 6.7% of the time. Most of the time, if you're randomly selecting a ball, it's going to be just fine and be underneath the 290 yards. But they're saying, what if I want to be 99% sure that a randomly selected ball will not exceed the maximum distance? So in that case, what we're saying is, we want to have this mean. What's the largest mean that the distance should be set to in order to have the manufacturing process meet that goal? So we're saying we have an unknown mean, but still 4 as the standard deviation, right? And we know that if I set the boundary value here to be 290, because we can't exceed that, we want to be 99% sure that we will not exceed the distance. And that means that the area to the left is going to have to be 99% this time, instead of, let's see, this was like basically 7%, so it was 93% before. Okay, so basically we're adjusting the mean downward to try to make this area to the right be smaller than the 6%. Okay, The question is, how do we solve this, right? We have inverse norm and normal CDF that we can use if we have a known mean and a known standard deviation, but we don't have that. We have an unknown mean here. Okay, so what we're going to do is we're going to take we're going to look at the standardized curve. In other words, if I take all this data and ran it through the z formula to get z-scores, then it would have exactly the same shape, but the mean would be 0 and the standard deviation would be 1. Right? And so what I can do is I can look at this data value that's 290 and call that the x value. That's the data, right? But if I can find the equivalent z-score value, then I can use the z-score formula to link the two. So I know that there's also a z-score associated with the same spot. That is 99% of the sure that we're not going to be above the value. Right? So now to find this z-score value, I can use inverse norm. That z value would be inverse norm. 99% of the time has to be to the left, with 0 as the mean and 1 as the standard deviation. And when you plug that into a calculator, you end up getting 2.3263. I always round to 4 decimal places. Now here's how we put that together. What we're saying is this x value of 290 is connected with this z value of 2.3263, right? And I have a formula here for relating those. The z-score is x minus the mean, the data value minus the mean divided by the standard deviation. So if I now know that the z-score is supposed to be 2.3263, and the data value that goes with that is 290, and we don't know the mean, but I know the standard deviation is 4, then I can plug all those 3 values in and solve for the mean. So all I would do is multiply both sides by 4, actually, and that turns out to be 9.3052 equals 290 minus mu, and solving that for mu, for the mean, turns out to be 280.6948 yards. All right, so if we set this mean to be 280.7 yards about, that's lower enough to make the tail on the right-hand side drop to only 1%. Okay, a tricky problem. Okay, let's try the next one. There's 2 more. This one says, a restaurant owner reports that 5% of the time her restaurant is serving less than 20 people, and 30% of the time her restaurant is serving more than 100 people. If the number of people being served follows a normal distribution, what would the mean and standard deviation be for this distribution? So pause the video and give this one a try. Okay, to solve this one, we're going to do something very much like what we just did on the previous example. We're going to use standardized versions of the values as well. I'd like to picture it like this. I have in the actual data, there is some mean and there is some standard deviation, but I don't know either of those things at this point, right? I do know, though, that 5% of the time, so 5% of the time, we're serving less than 20 people. So 5% of the time, this area being 5%, we have less than 20 people being served, okay? Also, we have a second piece of data. We know that for whatever this mean and standard deviation are, we know that 30% of the time we're serving more than 100 people. So 30% of the time we're serving more than 100 people. So that gives me a way to kind of think about that. Unfortunately, I can't directly solve these things because I have an unknown mean and standard deviation. But to force me to have a mean and standard deviation, what I can do is use the standardized version of these curves, right? I have a standardized version of that with a mean of 0 and standard deviation of 1. And I can use those same values, but now I'll have a matching z-score for this. Same thing here. I'll have some place which has a z-score that has 0.05 below that, right? Okay, so let's work on each of these. The z-score here would be the inverse norm. We have to have area 0.05 to the left, so 0.05 to the left, using 0 and 1. And if you plug that in a calculator, that z value turns out to be, let's see, that is negative 1.6449. And over here, this z-score is inverse norm. If there's 30% to the right, then there's 70% to the left, right? So we would have 0.701, and that z-score turns out to be positive 0.5244, all right? Okay. And so now what I can do is link each z with its corresponding x value, its corresponding data value, because I have the z-score formula, right? Z is x minus the mean over the standard deviation, data minus the mean. So if I took this first pair, right, this z-score here is connected with this x-score here. It means that if I plug z of negative 1.6449 in, I get that's tied to an x value of 20 with my unknown mean and standard deviation. I could solve and rearrange this. If I multiply by sigma and move the mean on the other side, it would end up forming this equation right here. Mu minus 1.6449 sigma equals 20. So this is an equation, right? From just kind of rearranging the terms into a mu term, a sigma term, and a right-hand side number. And then for the other one, I have the data value x of 100 is linked to the z-score of positive 0.5244. So that means that when z is 0.5244, the data value is 100 with that same mean and standard deviation. And if I rearrange that one, it would be mu plus, good Lord, mu plus 0.5244 sigma equals 100. So that gives me a second equation. Okay. What I can do now is treat this as a system, and I'll solve this system for the mu and the standard deviation. So if I think of this as a system of two equations, I have mu minus 1.6449 sigma equals 20, and I have mu plus 0.5244 sigma equals 100. If you thought of that as a system, you could use either elimination or substitution, or my preferred method is using augmented matrices and RREF. So if I did this, I could make a mu column here, and then I would have the coefficients negative 1.6449 and positive 0.5244 with right-hand sides of 20 and 100, right? And I could plug that into a calculator to do matrix manipulation here. So see if I can move this around a little bit. Okay, so I want this over here. All right, so what we could do is we could turn on this. We could go to a matrix menu and call up matrix A and make it a 2x3 matrix. Enter the coefficients, 1, negative 1.6449, and 20, sorry. Read my own handwriting there. And then 1 and 0.5244 and 100. And then I could, let's see, is that right? Yep, okay. Then I could quit out of that, go back into the matrix menu over here to math and scroll down to reduced row echelon form, or REF, and run that on matrix A. And that would give me this number here. So once I do RREF, I get, I'm just going to copy the matrix here. I get, after doing RREF, I get this matrix, which would be 1, 0, 0, 1, and then, let's see, is this right? Yeah, it should be, I don't think that matches, 80.2. I got a different number when I ran this before. Let me make sure I had the original matrix correct before we go any further. So the original matrix was supposed to be 1, negative 1.6449, and 1, positive 0.5244, 5244, yep, 20 and 100. Right, okay, so I can trust these results. This should be 80 point, I'm going to round 80.7 and 36.9. So 80.7 and, what was it again? 36.9, 36.9. Okay, since this is the mu column and this is the sigma column, this equation is now 1 mu equals 80.7, and 1 sigma is 36.9. Okay, so what this is saying is that this distribution that we were trying to figure out, see if I can rotate this back down again, this distribution, the unknown mean and standard deviation are, the mean is actually 80.7. So on average, this restaurant serves 80.7 people with a standard deviation of 36.9 people. Okay? All right. Let's take a look at, I think this is the last problem. Yeah, okay. So it says in 2004, New York public health officials reported that 22% of adults smoked, and they increased the sales tax on cigarettes in order to reduce the rate of smoking. A year later, they checked a random sample of 1,000 New Yorkers to see if the tax increase had a significant effect. What would the number of smokers need to be in this sample to convince you that the rate increase worked to significantly decrease the rate of smoking? All right, so pause this one to give it a try. All right, so this is an interesting problem. If we were to analyze this properly, it really would require a binomial solution. So I'm going to do it that way first, just to give some insight into how we're going to then use the normal approximation to the binomial to solve the problem in another way that's easier, okay? So really, this is, if you watch the videos on the binomial, right, we would say, do we have a yes or no situation? Yeah, yes in this case is that someone smokes or smoked, right? And then do we have a constant probability? The probability seems to be 22% for any individual person to smoke in New York here. And then what about the trials, right? Well, we have specifically 1,000 New Yorkers, right? So that means we have a fixed number of trials. N is 1,000. And that makes this a binomial setting, right? This is a Bernoulli trial setting with binomials specifically. So we could do a binomial solution for this. We could define a random variable x to mean the number of people who smoke, right? And that could be in a sample of 1,000. None of them could smoke, one of them could smoke, all the way up to all 1,000 of them could smoke, right? Any of those are possible answers in this discrete probability problem, right? So the question is, it asks, what would the number of smokers need to be in this sample to convince you that the rate increase worked, right? So what would we expect? Well, we expect 22% of adults smoked, right? So 22% would be 200, like if I took 1,000 and I multiplied by 22%, that would be 220, right? So somewhere out here is 220. This is kind of what we might call the expected value. We would expect that, right? In other words, if we had 220, that means the percentage is still 22. The question is how low would the probability, what would the number have to be decreased to before we would be able to say, yeah, I'm pretty sure this worked, right? In other words, what if this decreased to, say, 100? Would that be enough? Could it decrease to just 200? Something like that? So one of the ways to kind of think about this is to say, you know, how likely is it that we would have a certain number that smoked out of this 1,000 just randomly? Like if this had no effect at all, if the tax increase didn't have any effect, and we would just had 22%, you know, if I took a random sample of 1,000 people, I might get exactly 220, but I'd likely get some number near there, right? Like it probably wouldn't be surprising if I got 230 or maybe 215, right? The question really is, how likely is it to get a number that's a certain number or less, right? How likely would it be true to happen? So what I could do, and this would be really cumbersome, is I could pick a number like this. Like I could say, let's pick a value, like say, let's do 210. Okay, I'm going to pick a number here, 210. This is not the way to solve the problem, by the way. This is just showing you why we need to solve it in the other way, because this is so cumbersome. So I could pick a number like 210 and say, okay, what's the probability that we would have 210 or more people in a sample that would have that number of the 1,000 that smoked, right? And we would say from binomial that the left-hand probability and the right-hand probability add up to 1. So this probability to the left over here could be modeled with a binomial CDF function. and we would say out of 1,000 people that smoked, if the chances of smoking are 22, what's the probability that we would go up to and including 209 people? And on the right, if we wanted this probability, we would just do 1 minus the left probability. So let's just calculate that really quickly, right? That would be 1 minus the binomial distribution CDF function. If we had 1,000 trials where there's a 22% chance that someone smoked, and we wanted to know up from 0 up to 209, so we could subtract that, right? So that probability would be 78%, right? There's a 78% chance of that happening, right? That's, I think we would have to see that that probability drops, right? Well, it'd actually have to be, the right-hand probability would have to be, really high. Like maybe we would say, like what we're saying is if this probability is 78% of the time, then this probability would be the other 22% of the time, 22% of the time, right? So how would that have to change? In other words, if I picked another number, like if I picked this number down here, right, then maybe this number would drop to say 10%, and this would become 90%, right? And if I picked a number low enough, here, maybe this number would drop to say 5% chance, 95% chance, right? So at some point, the number is low enough that there might be a really unlikely to occur just randomly. And it would be so unlikely that we would say, it must have been due to the tax increase, right? So what we can do is we can pick a number. Now, if you've taken an AP statistics class in the second semester, we talk about the fact that 5% is sort of the industry standard number for if something is 5% or less likely to occur by random chance, then that means that it's probably attributable to the thing that you believe is the cause of the effect that you're noticing, right? So what I could do is I could keep guessing numbers here, just guess different numbers to plug in here over and over and over again until the left probability turned out to be only 5%. But that's kind of an inefficient way to proceed. So rather than doing this by guessing different numbers and trying things with a trial and effect approach, we're going to do something different. This illustrates why we need sometimes to model binomial problems by normal functions. So in the lessons, we found that if the sample size is high enough, if this is large enough, then we can approximate the binomial distribution with a normal distribution. Okay, so what's the criteria for that? Well, the criteria is you have to have the number of successes and the number of failures have to be at least 10, So the number of successes, that is n times p. In other words, if we have 1,000 people in the sample and we expect 22 of them to smoke, that would be 220 people smoke, and that's definitely larger than 10, so that means the sample size is large enough for that. The number of failures is sometimes called NQ, so that would be 1,000 times the other percentage, right? So if there's a 22% chance that somebody smokes, there's a 78% chance that they don't smoke. Right? And that means that would be 780 people. And both of those are over 10, so it is okay to use an approximation. It's okay to approximate. Okay, now if we are going to approximate, then that means we need to say we're going to use a normal curve to approximate this really truly discrete probability problem. We need to know what the mean is and what the standard deviation is. Okay, so the mean turns out to be n times p. It's just the expected number of successes. Yeah, it makes sense. If we have 1,000 people that in the sample and 22 smoke, we would expect that most typically 220 people to be the number of smokers here. What isn't intuitive is the standard deviation turns out to be the square root of n times p times q. So that would be the square root of 1,000 times the probability of success, 0.22, times the probability of failure, 0.78. And if you plug that in a calculator, that turns out to be 13.0996. So that would be here, 13.0996, 13.0996. Okay. Right, so if I just kind of take 220 and add 13, this spot here would be roughly 233, and this spot, 220 minus 13, would be at 207. So a lot there's a big chance of having between 207 and 233 smokers in that group. Once we start deviating beyond those values, it starts to be less and less likely. Okay, so now what we're going to do is we're going to say the industry standard says as long as we have a less than 5% chance of something happening, then that means that we think it's likely to be caused by the thing we're investigating. So this was trying to drop the number of smokers. So we'd be on the low end, right? And we'd want to know where would we have to be down here for us to say that there's only a 5% chance that that happened randomly and was just because normal variation. So this distribution represents the normal amount of variation we would see whenever we sample 1,000 New Yorkers and count how many smoked. Okay, so what would this boundary value be? Well, that's where we use our inverse norm function. So inverse norm, 5% to the left, that's my arbitrary decision point to say if it's 5% going to happen by chance, then I call it significant. If the mean is 220 and the standard deviation is 13.0996. Okay, and if you plug that in a calculator, that turns out to be 198.45. So basically, I'm going to round it down and say I would have to have 100 and if I saw 198 or fewer smokers out of that sample of 1,000, then that would tell me that the smoking rate has definitely lowered. I mean, it's very likely that the tax increase had a significant effect. All right, so that's some kind of good sampling, a cross-section of the kinds of problems you can solve with the normal curve in various ways.